Okay, that's fine. So, good morning, everyone. Today we are here to have this talk by Celso Villas-Boas. Professor Celso Villas-Boas is a full professor in Brazil. He worked a long time ago with Professor Jaha Hemp from Max Planck, Celso.
Yes.
Yes, so he was a postdoc there. So Professor Celso Villas-Boas is now at UFSCar, it's a Universidade Federal de São Carlos, and Celso accepted to give a talk about photons in the darkness. So hope you enjoy, guys. Celso, again, thank you so much for accepting our invitation. Yeah, so we can start. Thank you again.
Okay. Okay, Alan. Thank you so much for the invitation. It is a really pleasure to me to be here to talk to you about these results, about these ideas. So I'm really happy to discuss with you because I know that you are in a very strong group of quantum optics group. So basically, everything that I'm going to talk here today goes to the very fundamental aspects of light matter interaction. So I know that in your group, you have many experts on this topic. So I have been discussing these results with many people, and I'd love to discuss with you too. So I would love to have your input, your criticisms, your comments about these results, because for me, it's very interesting. For me, for Gerhard from Max Planck, we are very, we believe that this could be very intriguing results. So your opinion is very valuable for me. So please feel free to comment, to stop me, to interrupt me at any time during this talk to discuss, to go into details about these results. The main idea of this paper, of this talk, can be seen in this picture here that describes one of the most basic experiments we have in physics, that is the double slit experiment. So we have photons coming from one slit or from the second slit here. And according to the classical interpretation, we have points where we have maximums and minima. So the points where we have maximum here, we have light. So in the points we have minima, so the dark spots, according to the classical interpretation, we have no photons or no light reaching those points. And the main message of this talk is I'm going to try to convince you that in those spots, dark spots, indeed we have photons, so we have light, but they are in a such state that cannot be detected by the detectors. So it's very opposite compared to the classical interpretation. So classical says that there is no photon at that point in the dark spots, but according to the theory I'm going to explain you today, we have photons, so we have light. This is why I decided to put the title of my talk, Photons in the Darkness. So in this darkness point, we have photons. So I'm trying to convince you about this. So please feel free to comment to be against or in favor of these ideas. So basically the results I'm going to show you is basically in this first paper here. This first paper has a long history. I started discussing this paper very in the beginning of the pandemic in 2020. I started discussing with Gerhard, and then we discussed it until the end of the 2021, and we came up with a first version, but that version of the paper was with some points very unclear for us. And then since 2021 until the beginning of this year, I have been discussing a lot of this paper with Gerhard. So he came to Brazil one time here, we discussed it a lot here. I went to Munich a few times to discuss with him again. And then in the beginning of this year, in March of this year, we could finalize these discussions, and then we came up with a new version that is the version that is submitted nowadays to PRL. So we already have some comments of referees. Two referees already gave us their reports. One of them found the results very interesting and recommended publication. The second one said that both said that the results are correct, but the second said that there's anything new in this paper here. So according to the second referee, he said that basically everything that we are showing here was already predicted by Glauber's theory. Of course, I do not agree, but of course, I'd like to hear from you if you agree with the referee or with me, in other words. Well, since then, we also did some parallel works. One of them was together with people from Stockholm, the group from Professor Marcus Heinrich, and they're working with trapped ions. So trapped ions in two-dimensional traps. We could observe the results we are showing here. So all these interference aspect between two different modes could be observed. Indeed, we observed in a trapped ion system. So all the states we are showing here was experimentally built in a trapped ion system. So, and we could observe the effects predicted in this paper here. There are many other extensions of these papers. For instance, we showed how to use these dark and bright states to propose a universal quantum computation using cross-cavity systems, basically the system that Gerhard has in Max Planck. Also using the same cross-cavity system, we showed how to use this dark and bright state to build a kind of beam splitter for those states. So we can have a system that can reflect the bright state and can transmit the dark states. So the idea is very simple. And this paper was finished very soon, a few months ago. So there are other results that I'm not going to show you here, but are in progress. So I hope that by the end of this year, we'll still have one or two papers more related to these topics here. So, but basically, the idea of the results of this work is to understand a little more about what is light. So what is light is a very old question. So people have been thinking about this since the Greeks. So Aristotle and many other philosophers from Greece, and many years before Christ, they were thinking about how we could observe objects and how we can see things around us. So they are trying already to understand what is light, how can we observe, how can we see things. So they made many different theories about that. Of course, I'm not going to describe all of this. So in another talk I can discuss. So it's very interesting how they used to think about the light. But going very short for the history about light, the most famous discussions about what is light was made by Huygens and Newton, so many centuries before. And the first claiming that light is a wave because of the interference effect and many other things. And Newton claiming that light would be described by particles. So the corpuscular nature of light by Newton against the Huygens wave description of light. So as you know, we had many contributions from many other scientists throughout the history here. And then basically with the experiment carried out by Thomas Young, and then with the theory of James Maxwell that could describe the electromagnetic equations and then the wave equation for light, for the electric field and for the magnetic field. Then with those experiments for Thomas Young's and with the theory of Maxwell, basically people decide to forget about the corpuscular nature of light. So since that time, at that time, people decide to describe light only in terms of waves because of all of this. But as you know, the history changed when, with the origin of the quantum mechanics theory, so with the works by Planck and then mainly by Einstein. with Einstein, when he made a theory to describe the photoelectric effect, he again came back with the idea of particle of light. So the smallest part of the light that later on was called by I forgot the name of the guy, called by as photons. And then the particle theory for light is back again. So as you know, these two theories about light, the wave description and the particle description of light, gives the origin of the wave particle duality for light. And then de Broglie proposed the wave particle duality for matter, as you know. And then with this, we came up with the Schrödinger equation. So, but later on, more than 40 years later, after the Schrödinger equation, as you certainly know, Lamb and Scully, they made a very nice paper describing all the photoelectric effect in terms of a semi-classical theory. So assuming that the device, the material here, is composed by atoms with discrete levels of energy, but assuming that the light is classical, continuous, no particle in his theory, they were able to show that the photoelectric effect can be explained without assuming that light has photons. So without this idea of particles of light. So this is interesting because all the development of quantum theory relies on the wave-particle duality of light. And then somehow the quantum nature of light has been discovered at his classical limit. This is something interesting. But in the end, the question is, indeed, we can say that light is made of photons or no? Well, the modern theory, for instance, as we saw in the Harosh experiments, he proved that somehow we have indeed photons in the light field. So for instance, in this very nice experiment he carried many years ago, he could see that starting the cavity mode with, for instance, 4 photons, after some time we go to 3, go to 2, 1, and 0, and so on. So there is no 3.5, 2.5 photons here. So this is a clear evidence that indeed we have particles composing the light. So, and there are many other results that prove that somehow we have indeed photons in light fields. So all of this was observed in the limit of a few photons. One natural question is, could we still observe quantum aspects of light in the limit of many, many photons? I'm not going to detail on this paper, but we addressed this question many years ago, and we came up with this idea where we could show that even the limit of very strong fields, here are about 100 photons, but in another paper, we extended these ideas to millions of photons. We still can see some signatures of the quantum aspect of light, even for really intense fields here. So based on the concurrency or the quantum correlations that can be generated between two atoms interacting with the same photon here, with the same mode. Well, going back to the idea of Einstein here, the photoelectric effect. The photoelectric explanation given by Einstein was very beautiful. Many people loved it. Indeed, he got the Nobel Prize for that. But at that time, many people was against his ideas. And one of the main objections against his idea was made by Robert Millikan, in 1916. So what was the problem pointed out by Millikan? He liked the idea of photons, of particles of light, of the explanation that Einstein provided for the photoelectric effect. But according to Millikan, this idea of particles would be impossible when we compare to the other experiments we have, and mainly about the interference experiment. Because according to Millikan, the corpuscular nature of light would be in a complete conflict with the aspect of interference. In other words, according to Millikan, we would never be it would never be possible to explain interference aspects in terms of particles. So because interference aspect, according to Millikan, is only a nature of wave only. And this is one point that I'm going to try to convince you that his ideas of Millikan was wrong. And going back to this idea of Millikan, the main question that I'd like to answer here is, can we explain the interference pattern in terms of particles? Let's go back to the double slit experiment. So let's take here, assuming that firstly, the classical interpretation of the interference. We have an electromagnetic field here. So this field can cross two slits here. One slit, that give origins to two fields here. One comes from this direction with a specific wave vector that I called K, and another that comes from another point. So they are in a different positions here, and they are reaching the same point on the screen. So the first wave has a wave vector K, the second wave vector K prime. So, and in a given point here, we can have the resulting electric field here given by the sum of both, according to the classical interpretation. And in the dark spots, so in the points we have destructive interference, the sum of the electric field is zero. So in the classical interpretation, we do not need to take into account the detector to explain the absence of light. So there is no light there because the electric field there is zero. So if you try to explain in terms of interaction with the detector, we have to go to the light-matter interaction description, so the dipole interaction. And here's clear, if the resulting field ER is zero, of course, the Hamiltonian here would be zero, so that means that no light would be detected here. So in this case, we can describe the detector as the smallest system, so just a two-level system or a single atom. But of course, the detector is made of many, many two-level systems here. But in a sense, they are described by two-level systems. If you go to the quantum description of the same experiment, so for simplicity, let's assume that we have just a single photon coming here. So this single photon can cross the first slit and goes in this direction. So we have wave vector K, or could go from the second slit, goes into this direction here with a wave vector K prime. So we can call this first mode A and the second mode B. So as this is really important, as we have different wave vectors, because they are coming from different positions, reaching the same point on the detector on the screen, we have indeed different Hilbert spaces. This is not my idea. This is the idea given by Glauber and Scully and Zubair. So we can see in their books, these descriptions. So the state of the field after this double slit here would be described by something like this. One photon in the mode K, following a path, KR1, plus the same photon could be in a superposition in the second mode, K prime, following a different path here, R2. So in other words, you can describe this in a more precise way as one photon mode A, zero in B, and a phase factor here that depends on the path, R1, plus zero photon A plus times one photon B, following a different phase here that comes from the path R2 here. So if this light is detected on the detector, so if you can see light on the screen, that means that the photon is absorbed by the screen or by the detector, and one excitation is created in the screen or in the detector. So in this case, to describe this process of detecting this light on the screen or on the detector, of course, we have to go back to the light-matter interaction. But in this case, in a quantum description of this light-matter interaction. So in this case, we have the operator that describes the electric field E, written in terms of A plus and A minus operators. And the interaction between the modes with the detector or with the two-level systems of the screen or the detector can be described by this Hamiltonian, that in essence is basically the Jaynes-Cummings Hamiltonian. Okay, so this is what was described by Glauber, and he got the Nobel Prize for that. But then comes the interesting point. In case we have a single mode, assume that we have just a single mode, not two modes, as we have in the double slit experiment, but assume that we have just a single mode in the field. That means that we have just a simple Jaynes-Cummings Hamiltonian, and the operator A plus is just proportional to A, the annihilation operator of the mode. So A plus times psi equals to 0. So what are the eigenstates of this operator that give us 0 eigenvalue? For a single mode, there is only a single state, that is the vacuum. That means only the vacuum is unable to excite the detector. So if you have a single mode in any state different from the vacuum, we could detect light. So you could observe the light there. But the situation becomes interesting when you go to two modes case or more modes. For instance, here for two modes, the A plus operator is described by A plus B. So the annihilation operator of the first mode plus the annihilation operator of the second mode. And in this case, what are the eigenstates of the system with 0 eigenvalue? Of course, the vacuum is one of them. So the vacuum is unable to excite the detector. But there are many other states. And this is the interesting point. Because, for instance, here, we have one photon in mode A, 0 in B, minus 0 in A, 1 in B, is also an eigenstate of the operator A plus with 0 eigenvalue. That means such state cannot excite the detector. So this means that the photon is there, but in a state that cannot be detected. And there are many, many, many other states. I called here psi n0. So n goes from 0 to infinite here. So there are many states that behaves in the same way. That is, they have photons, they have energy, but they are unable to excite a two-level system. So they are unable to be detected by a simple detector. Such kind of states already appear in the literature. So one of the referee called my attention that states like that I call binomial states. There are many, many, in fact, references like that, studying the properties of those states. But I didn't find a single paper using such states to describe the interference effect. So, and the main message of these states is this one. So they are states with photons, but they are unable to exchange energy with the detector. So they have photons, they have energy, but cannot be detected. This is why we called, instead of binomial states, instead of binomial states, we decided to call them dark states because the photons are there, but they are not, cannot be seen by us, by the detectors. Well, going back to the interference effect. Remember that we have this state that describes the photons that arrives in a single point here in a detector. And the state is like this, 1, 0 with this phase factor plus 0, 1 with this other phase factor. And the point is, whenever you have difference of paths equals to 2 times n plus 1 times pi, so this is exactly the point where, according to the classical interpretation, we say that we have destructive interference. So no light is arriving there according to the classical interpretation. But according to this theory, the resulting state, when we have this difference of phase, is just this one, 1, 0 minus 0, 1. So in any point where we have such a difference of phase, we have states like this that are dark states. That means, the eigenvalue of this state is 0. So they are not able to excite the detector. If the detector is in the ground state initially, the detector will remain there when the light arrives there in such state. Well, in an interference pattern, we have, besides the destructive points, we have the constructive points, so the points where light is detected. what happens in those points? In those points, we can describe the interaction in terms of James Cramer's Hamiltonian. So basically, in the case we have a single mode, if you instead of having two modes, we have just a single mode, the exchange of energy would be given by the coupling between the mode and the detector times square root of n, where n is the number of photons we have in the mode. So as bigger the n, the higher the exchange of energy, the rate of exchange energy between the atom and the detector. So the higher the rate of exchange energy, so that means that more light is scattered. So this is why when we send just a single photo, it's really hard to see the spots, the bright spots. But when we send a very intense laser field, we see clearly why we have light scattered in those points. But what happens when we go to multimode case? Again, if you have two modes, instead of having g square root of n, for two modes, we have g square root of 2n. So that is an increasing in the rate of exchange of energy. So even for a single photon, so if n is equal to 1, even for a single photon, the rate of exchange energy will be higher than the single mode case. That means in the points where we see light, we have more light being scattered per time. So even for a single photon. So, and there are many other states that behaves like this. So one is the 1, 0 plus 0, 1. So, but there are others with 2 photons, 3 photons, and any photons with n going to infinite again. And then again, the number of photons in each state here is the same as in the previous case. So in the dark state, we had 1, 0, minus 0, 1. In that case, we had just 1 photon on average. In this bright state, we also have 1 photon on average, but the difference is that this state will be coupled to the detector. So we can detect light when the modes are in this state, but we cannot when the modes are in the minus state here. So this is why we decide to call this state as bright state, because they can absorb light, they can exchange light with the detector, so and then they can scatter light. So we can see the scattering of light when the modes are in those states. So in fact, there are many different kinds of states. So when you go to the collective states of these systems, we have on the right here what we call the dark states, and here we have the bright states. But there are also other states here we decide to call intermediate states, because they are not bright or nor dark. So this is the full set of states that we can have for 2 modes. From 3 or more modes, this becomes even more interesting. We are finishing another paper describing the multimode case. But with this, we already can explain in more detail the interference. Because if you have, again, the state psi after the double slit is described by this, and then we can have difference of phase as 2 times n pi. So in this case, we have according to the classical interference, we have the constructive interference. But in this case, the state we have is 1, 0 plus 0, 1. So in this case, we have the rate of exchange energy is multiplied by a square root of 2. So we have an increasing of the rate. So we have a strong exchange of energy. This is why we see more light scattered in the bright points. Everything that I did here so far is assume that we have just a single photon. So all these ideas, how they can be used to explain the case when we have a coherent state. So a state with many, many photons. So instead of assuming that we have just a single photon, let's assume that we have a coherent state that is a superposition like this. That is basically the state that describes a good laser. So in this case, there will be some photons come from one path, another photons come from another path. So in the end, we will have a difference of phase here. So his k prime should be prime here. So there is a difference of phase that depends on k r1 minus k prime I2. So in fact, his should be the delta phi. Sorry, the delta phi is here. So in the end, what is the point? Whenever we have delta phi equals to L pi, L is an integer, 0, 1, 2, and so on. Alpha, the state we have is equivalent to the constructive interference because we have two in-phase coherent states, so alpha and alpha. But the interesting point is when we have in-phase coherent states, we can decompose such states in this basis of bright and dark states. And interestingly, we have here only psi n, that is superpositions of only bright states. So there is no intermediate state or bright state, dark states in the points where we have maximum light. On the other hand, when the difference of phase is 2L plus 1 pi, so the destructive points, according to the classical interpretation. So in this case, we have alpha and minus alpha. That in this case, it's clear. Classically, the amplitude of the field is alpha plus minus alpha is 0. So there is no field according to the classical interpretation. But according to this theory, this state can be written as a superposition of dark states only. So there is no projection on the bright states. So that means that both either in the maximum or in the minima points, we have the same number on average of photons. Doesn't matter if we are in the bright or in the dark spot. In both cases, we have on average the same number of photons n, but the difference is, in this case, we have only bright states, superposition of bright states that can be detected, and in this case, only dark states that cannot be detected, because that is the eigenvalue of those states are all of them 0. So this means that, according to this theory, in the dark spots, we have photons, we have energy. So this is why I said there are photons in the darkness. Of course, everything that I explained to you so far can be explained in both ways, with my theory and with the theory described by the standard interpretation of interference, the classical interpretation. But this happens because whenever we have dark states, the electric field, the resulting electric field, if you sum the electric field A of the first mode A plus the electric field of the second mode B, for any dark state, the resulting field is 0. So this means completely equivalent to the destructive interference. So no coupling between the modes and the detector. When we go to the bright states, the resulting field in any bright state is different of 0. So that means that we have indeed a new field there. So that means we have constructive interference. That means coupling with the detector, and then we can detect such light. But can we find some state that could predict something different? And then we came up with this state here. We call epsilon state. That is two modes, one in a state 0 plus 1, and the second in a state 0 minus 1. If you take here, the total electric field of this state is 0. So that means that if you take it, and it's quite clear because here we have one electric field with a phase plus and the other one with phase minus. When we sum both, gives 0. So according to the classical interpretation, this kind of state would be undetected by detectors, by our eyes. But if you try to evaluate this state, so if you describe the interaction between a two-level system, then we could see that the Hamiltonian, the Jennings-Cummings, for these two modes, applied to this epsilon state would be different of 0. So according to Glauber's theory, such state could be detected. According to classical interpretation, could not. But according to Glauber's theory, this could be detected. Why? it could be detected. It could be detected because indeed the epsilon state can be decomposed in a portion here that is dark, another one that is dark again, dark with two photons, but there is a projection on the 2-2 state that is a bright state. So according to our theory, indeed this kind of state could be detected. We would detect light on this mode, on this state, because there is a projection on the bright state. So this is a clear evidence that classically we have some predictions and this theory predicts something different. So this could be observed in an experiment. Indeed, this was done in Stockholm, as I said. One of the consequences of the results I showed you so far, that for me is very interesting again, I'd like to hear from your opinion about that, is when we describe the path detection in the double slit experiment. Because when we don't have detection of the path, so we do not put an observer detecting for which slit the photon passes here, we see an interference pattern here. So, but whenever we put a detector, but please pay attention, this detector is assuming that is such detector that cannot modify the path of the photon. So it's a non-destructive measurement that could observe the photon, but does not modify his wave vector in somehow. So that means that if you put the detectors here, we know that when we know from which slit the photon passes, we destroy the interference pattern. This is our experimental results. We can find this paper here, very recent. It's a didactic paper. But according to the theory I explained to you, whenever we have a single photon crossing the slits, if there is no detection, means that there are points with maxima of light. In those points, we have states like 1, 0 plus 0, 1. And there are points where there is no light. According to the classical interpretation, according to this theory I present to you today, we have photons, but in such state that is 1, 0 minus 0, 1. So the light is undetected there. But the photons are going to that point. This is really important. This is important. Why? Because when we introduce the detector, what is the role of the detector? To generate an entanglement between the state of the detector and the photons and the modes. Whenever we have this, when we trace out the variables of the detector, that state that initially was a bright state, a pure state, becomes a mixed state. This mixed state has projections on bright and dark states. So light will be detected there. But on the points where in the beginning we would have zero detection, that is a dark state psi 1, 0, in that case, when we trace over the variables of the detectors, we end up with basically the same state of the mixed state as in the previous case. And again, this guy has projections on the bright state, so light can be detected. So the photon never changes the path, the wave vector. The photons are always reaching the dark spots. But now, with the presence of the detector, we can detect such photons because they are in such a state that can be detected. So this is the main message here. Photons always go to the dark regions, but are detected only when the dark state is destroyed. In this case, entangled, generating an entanglement between the modes and the detector. We use such states for some good applications? Yes, one of them is this one. Sorry for this mistake here. We showed how to use such states to produce logic gates. For instance, C0 gates, Fredkin gates. And the idea is quite simple. Whenever we have the input field in a dark state, they do not interact with the atom. So they enter the cavity and go out without any modification. On the other hand, when we have photons in the bright states interact with the atom. And when the atoms are in a strong coupling regime, the photons cannot enter the cavity, so the photons are reflected immediately getting some phase. So in the dark state, photons enter and go out without any modification, without any phase. But when the photons are in bright state, they got a phase. For instance, we could show here how to implement a single shot Fredkin gate as this table here, or even CNOT gates. Of course, in this case, the atom is a qubit too. So the modes are in qubits, and the atom is the other one. So in this case, three qubit system. We also showed how to use this to generate a kind of beam splitter for dark and bright states. The idea is basically the same. So imagine that we have here a cross-cavity setup. The light can enter in this direction, it can go out in this on the right, or it can enter here on the bottom and go out in the upper side here. So imagine that you have a superposition of bright and dark states. The bright cannot cross the system, but the dark can cross. So in this case, we have a initial stage here coming in to the setup. All the reflected light will be superposition of bright states, and all the transmitted light will be only dark states. For instance, imagine that we have an input as one photon mode, one mode here, and 0 in the other. So the state 1, 0. 1, 0 is a superposition of bright 1 and dark 1. So in the end, we would have a transmitted light 1, 0 minus 0, 1, and a reflected light 1, 0 plus 0, 1. So that is entangled state indeed. So as I said, of course, all this theory is beautiful, but could be observed experimentally. As we know, physics is an experimental science. So without observing this, would be really hard to say that, in fact, these results are, in fact, right. And fortunately, we were able to do this experiment together with people in Stockholm, the group led by Professor Marcus Heinrich. And instead of having two light modes, we had in that experiment two motions, different directions of motion of a trapped ion. So in this case, we can engineer interaction like Dennis Cummings with two modes. So, and these are the results we showed here in this paper. And these are some results. For instance, when we have the state 1, 0 plus 0, 1, there is an exchange of energy between the modes and the ion in a rate stronger than the single mode case. So this is the single mode case. This is the two mode case. And whenever the atoms, the modes are in the dark state, 1, 0 minus 0, 1, there's no exchange of energy. This is the points here close to 0. We also did the experiment with the upsilon state, and we also could observe that there is an exchange of energy. To finish, we extended these ideas for multimode, because everything that I showed you so far is for two modes only. But of course, we can extend this idea for multi-slits. So, and this is really important because with multimode, we can describe any shape of a pulse. So Gaussian pulse or many other kinds of shapes of light. So, and using these ideas, indeed, we have many modes here. And according to classical interpretation, we have to sum the electric field at any point here. But at any point here, we have a superposition of dark or bright state according to the theory I'm presenting to you today. And indeed, this is really important to explain, for instance, what happens in a pulsed laser. Pulsed laser, as you know, we have a material inside an optical cavity and a modulation of the modes here. So we have a sum of different modes, so with different frequencies in this case. And this is a paper that we are finishing. I hope I can put on the archive by the end of this week. And the idea is basically to do an equivalence between the modes, the different modes we have in frequency in a pulsed laser, And in this case, we have the same frequency, but we have different paths. But in the end, we have a sum here of different modes with different phases. And here in the cavity, we also have the same, that is a sum of different modes with different phases, but in this case, time-independent phase. But in essence, it's the same thing, this case and this one. And then we could prove in this paper that whenever you have a cavity emitting photons in different frequencies, when we sum them, we have regions where we have light and regions where we do not have light. But according to our results, in these regions here, where we do not see light, in fact, we have photons, but this is very interesting. All of them are in dark state. So we have a region, time-dependent region, that is in dark state. So we have photons, but not detectable. And the regions where we have the light, so where we have the pulse, we have photons indeed, but they are in bright state. So in both regions, we have photons, but in some regions that can be detected, in other regions that cannot be detected. So to finish, basically the take-home message for you, dark states of light, they do not exchange energy with the detectors. When we have just a single mode, there is only a single dark state, that is the vacuum. So only the vacuum cannot exchange energy with the detector, with the atoms. That is clear why. But when we have two or more modes, there is an infinite set of states with non-null energy and non-null number of photons that cannot exchange energy. So they are there, but in an undetectable state. On the other hand, there are the bright states that can exchange energy with atoms, but they can exchange in a rate higher than the single mode case. And the increasing goes with square root of m, and m is the number of modes we have. Whenever we have destructive interference of coherent or single photons, the destructive interference can be written in terms of dark states only. The constructive interference can be written in terms of superposition of bright states only. So in the end, this is the main point. Photons are everywhere. So either in the bright spots or in the bright or in the dark spots, in both, in the same amount. What is different is the state, and this state makes the difference. Why in some points photons are detected, and why in other points the photons are not detected. So with these states of particle photons, we are describing the interference effect in somehow. This is why I claim that we do not need classical wave aspect to explain the interference, against the criticism of Millikan. So for independent modes, only the particle one, together with the superposition principle, which is not only for waves. Superposition principle is more general, is a mathematical principle, together with the particle description of light, and of course, with Schrödinger equation, we can describe without using the wave equation, the classical wave equation that usually we use to explain according to the classical theory. So this is my talk. Thank you so much for your attention. And I'm happy here to discuss with you.
Okay, so thank you, Professor Celso, for the very nice talk. So from my side, because we already discussed those things a lot, so I don't have questions, but if someone else have questions, please go ahead.
I have a question. Well, thanks for the talk, first of all, about how are you modeling your detectors? Like, are you assuming that your detectors can detect independently which one of the paths have followed the photons?
No, I'm assuming that I'm modeling the detector as a two-level system, okay? And this two-level system is interact simultaneously with both modes. So there is no way to distinguish between them. If we can distinguish, then we can detect independently the modes. In fact, this was what we did in Stockholm, because there we can artificially turn on and turn off the interaction between the modes and the detector. Because in that case, the interaction between the ion and the mode A or the mode B can be adjusted independently. But in a detector, as we see on a screen, in a double-slit experiment, for instance, there is no way to do this. So in that case, the atoms are interact simultaneously with both modes.
Okay, can you go back to the slide where you were like displaying the interaction between the Fock states and the detector? I think it was just before the one about coherent states.
Yes, I guess. Here.
Well, maybe a little bit after. Okay, yeah, that one, the one before, the one that you showed before.
This?
No, the one before. Okay, so when the light, so you have the two modes and they are both interacting with the detector, which is a two-level emitter. Then okay, how do you pick that normalization factor of square root of 2n? Because the two-level emitter can only absorb a single atom, a single photon, sorry. Like, where does the square root of 2 come from?
The square root of 2?
Yeah.
We have the James Combinaison, right? So we have just the James Combinaison interact, that is G, the coupling, times A plus B, times sigma plus Hermitian conjugate. So the square root of 2 comes from the A plus B applying to the state like this. So if you apply here A, the photon in mode A goes to 0. And when we apply B here, the photon in B goes to 0. And then we have a 0 plus 0 2 times. And then with this square
okay.
We end up with a square root of 2 in the top.
Okay, thank you.
More questions?
Okay, thank you for the question.
Someone else? No, so okay, so let's thank Professor Celso again. So thank you so much, Celso, for your time, for the very nice talk. And
okay, thank you so much for your attention, for your time. So I hope we can visit you soon, so we could discuss these ideas in person. I hope very soon.
Nice, it will be very nice. So thank you guys for coming. So see you next time. Bye-bye.
Thank you. Bye, thanks.
Thank you.